Hello and welcome to MT3. In the second of the tutorials on linear operators, still following Riley, Hobson and Bence sections 8.2, here we will look at the algebra of linear operators, and I will show you how a linear operator can be represented as a matrix. Okay, so what are we talking about here? Let's lay down some basics. Let's say we are in a vector space V. In this particular case, I've illustrated three dimensions to the space, but in general, let's say it's an n-dimensional space. And we've got a basis set ei hat, which spans this space. Okay, then we've got a vector, any vector x in this space. Now we apply some linear operator script a hat. Remember that, if you recall from the last tutorial, all linear operators will be designated by the script letter. It could be any script letter, but it's got a hat on it, and always capitals here, so we don't confuse linear operators with a normal orthonormal basis vector. Now, in general, as I said in the last tutorial, a linear operator can change the space. And I've tried to illustrate this here by showing you a space with a different color and a different number of axes in here. So the space which has dimensions n could become dimension m. Now, as far as I know, m should be less than or equal to n. I don't know of any examples of dimension increase, okay, but I could be wrong here, but m should be less than or equal to n. It doesn't matter for the time being, it's just that m is potentially different from n. This new space will be designated V prime, and it has a basis set Fi hat. Now these Fi's could be different from the Ei's here, and I've tried to illustrate this by showing you a kind of rotated frame here, but once again this is not so important. So the linear operator a hat operates on x in this space and gives you a vector y in this space. That should be a vector there. Now, in brief, what you can write this in a slightly different form, that the linear operator takes a vector space V and gives you another one V prime. The dimensions of this space is n, and this one is m, and the basis set I'm using here is E hat I, and the basis set in this prime space is F hat I. Okay? That's the general case. Now, quite often we will have linear operators which don't change the space itself. So often the space stays the same. So V is operated on by a hat, and we get the same space. Now this is the case when you have a rotation or a linear operator which simply lengthens each vector, so a stretching operator. Stuff like that could operators like these could keep the space the same. Now you've stretched the space, but it's the same dimension. The axes stay the same in these two cases, so we still have a dimension n, and the basis vectors here would be the same. And we'll come across these examples as a special case of the more general type here later. Alright, let's work with the general case for the time being. So, let's go back here. Back to the general case. So here we've got a hat operates on x and gives us y. Now let's write down expansions for each of these vectors, x and y. X belongs to V. Therefore, when we expand x in the basis set, it will look like this. I goes from 1 to n, xi e hat I. It uses the e hat I basis set. Y, on the other hand, belongs to the space V prime, Therefore, y is expanded in terms of the f hat I basis. And I'll use a different index here. And this goes dimension m, yj, f hat j. Okay? Now what I want to know is, given these expansions, is there something that I can say about the form of this operator A? Now you look at it, I need to know, every vector in the space V is written in terms of these basis vectors, E hat I. And from the definition of a linear operator, we know that A hat X is equal to A hat operating on the sum, I goes from 1 to n, xi, E hat I. Now this is a linear combination of vectors, and from the very definition of a linear operator, we know that a linear operator is in fact called a linear operator because when it operates on a linear combination of vectors, you can write this as the linear combination. Remember, xi is a scalar here, so it's a linear combination of A hat operating on each vector in turn. All right. So what I need to know now is, what does this operator do to each of the basis vectors? Now, if I knew how A operated on each of the basis vectors, then I could say exactly how it would operate on any vector in that space. Okay, and just to remind ourselves, this thing here is equal to y. So the next thing I want to do is to make a definition for how A operates on each of these basis vectors. And we're going to make a definition here. So A hat operating on E j hat is defined to be the sum I goes from 1 to m. Let's see if I get this and this is right. This is going to be A I j E. One second, I need to pause this here. I'll come back in a second. Hello, back again. I'm going to modify what I was getting at, and I just made a slight mistake here. So let's just erase some of the stuff. Yes. Okay. So what I want to do is to write. I want to know what A hat does to EI. So let's put this down here. It's easy sometimes to look at the hats and think both are basis vectors, but remember the capital script letter is an operator, and this lowercase letter with a hat on it is a basis vector. So A hat operates, the operator A hat operates on the basis vector EI hat, and that converts the EI hat into something which belongs to this new space, where the basis vectors now are these F's. So we will get every vector in this space V gets converted into a vector in the space V prime. Now any vector in the space V prime can be represented as a linear combination of the basis vectors of that space, and the basis vectors of that space are the Fj's. Now there are m of these, so j goes from 1 to m. And there'll be some coefficients here. We need to call these coefficients something. I'm going to call these coefficients a, and I need to give it this a subscript. That subscript which should depend on I, because there's an I on the left hand side, and should also depend on j, because there's a j on the right hand side under the dummy sum. Now I'm going to make a choice. This choice is going to have the j coming first and then the I. Now you'll see why later. Okay, so this is the definition. Let me just put some more space between these two. At J. And this is quite an important definition, so let's give it a box here with a star telling us that we really need that. Alright, so now let's use it. So we have y is equal to this thing here. The sum I goes from 1 to n xi, and then we have this thing in here which is given by this sum. So I'll put a parenthesis, and now we have another sum. J goes from 1 to m a j I f hat j, close parenthesis. Alright, so now let's get down here. Therefore y is equal to, what I'm going to do now is pull the sum over j outside and put the sum over I inside. We'll see why in a minute. J goes from 1 to m parenthesis. The sum I goes from 1 to n, and I'm going to rearrange the xi and the aj. So put the a j I first, then the xi, close parenthesis, and then have the f j hat. Now y itself belongs to the space v prime, and it's written in terms of the basis vectors of v prime. Y is equal to the sum, j goes from 1 to m, yj f j hat. So let's put that down here. So this itself is equal to the sum, j goes from 1 to m f j, yj f j hat. And now you can compare these two sums. Let's make a comparison here. We've got some stuff in the parenthesis, and then we have this fj hat. The stuff from the parenthesis should correspond to the yj. I'll tell you a little bit more on this soon, but let's just take it as it looks obvious and wave our hands a bit, as physicists often do. Therefore yj is equal to the sum I goes from 1 to n a j I xi. Now what I've done here, and this is pretty important again, what I've done here is to, once we know what these AJIs are, we haven't defined what it is, right? Let's just remind ourselves where this AJI came from. I said we will define this. By definition, by fiat, you would say that when this operator A hat operates on the basis vector EI hat, we will write this, this will convert the EI hat into a vector in the V prime space. The basis set used in the V prime space are these FJ hats. So this must be a linear combination of the FJ hats. And I've chosen the coefficients in this linear combination to be called AJI. A with subscript JI. Why does it need J and I? Because we have an I on the left hand side, so there must be an I here. And we are summing over J, so we must have a J here. Okay, so this is by definition. Yet I don't know what the AJIs actually are at this stage. I just have defined it to be like this. Once I have this definition, then with a bit of basic algebra, we've been able to relate the expansion coefficients for the vector y in the V prime space with the expansion coefficients for the vector x in the V space. So we now know how the vectors x and y are related, and they're related through these AJIs. Now we know that, so let's write this in what would be a traditional form, and then we'll see examples of what these terms are. This is a column vector. If you look at, we can write this in vector form as follows. This is the vector y is equal to, this is a matrix now. It's a 2-index object. It's a matrix. So I will call it capital A. It's not script A hat. It's a matrix now. A operating on the vector x. Or more graphically, remember vectors are represented as columns. So y1, y2 all the way to ym. This is equal to let me write this. I want to let's say x has a larger, this is the vector x, x1, x2 all the way to xn. That means that my matrix A is going to be rectangular, A11, A12 all the way to A1n, A21, A22 all the way to A2n, and this goes down to AM1, AM2 all the way to AMN. So this is a dimension M vector. This here is a dimension N vector, and this matrix has dimensions, it's rows by columns, so there are M rows and N columns. Okay, I'll just pause this a minute. Now what we have done is taken an operator A hat which operates on x and gives us y, where we introduce the basis for x and y. We have made a definition of what the operator A hat does to the basis vectors of the EI hat basis vectors, and we have then rewritten the operator equation in terms of vectors and matrices. Now you can write down the matrix form of an operator only when you have defined the basis sets for the space in which it is working. So the operator, let's put our original equation down. Originally we had y is equal to A hat operating on x. Now here the operator A hat is an abstract operator. I haven't yet defined what it does on the basis vectors. I can only do that once I have specified what the basis vectors are for this x space and the basis vectors for the y space. Once I have done that, then I can write everything down in a matrix form, a matrix vector form. So now the vector y becomes a column vector, the vector x a column vector, and the matrix and the operator A hat becomes a matrix A with this double bar under it. Okay, so what we need to do next, I'm not going to do it here, is to look at examples. In practice, how does one write down this kind of a matrix for a given operator, and what does this matrix look like? That's what we're going to do next. So thanks for watching, and we'll stop here.